Hello, I'm Xinyu from Tsinghua University. In this video, we will introduce our work, EgoLocate, which estimates accurate human pose, localization, and reconstructs the scene in sparse 3D points from a few body-mounted sensors. Our system requires only 6 initial sensors and a phone camera. The initial sensors are placed on the forearms, lower legs, head, and pelvis, and the camera is placed on the head facing outward. Such setup is compatible with recent VR devices, as many headsets are equipped with cameras. With the addition of a few IMUs, our system can be effectively deployed. Using the images from the camera, existing technologies can predict the camera's movement and reconstruct the scene points. They are accurate but not robust. On the other hand, using initial sensors, existing methods can estimate human motion. They are more robust for tracking, but have the issue of global position drift. We found that these two techniques complement each other. To this end, we propose EgoLocate, which combines inertial motion capture with camera tracking, maintaining the advantages of both. Here we show a live example of our system. First, our system needs a short period of movement to initialize. Then, the algorithm can simultaneously perform real-time human motion capture and sparse map point reconstruction. The black dots on the screen are the sparse points estimated by our algorithm, and their positions are continuously optimized during the tracking. Our contributions can be summarized as follows. First, we propose the first system that combines motion capture, localization, and mapping using sparse body-mounted sensors which runs in real time. Second, we design a tightly coupled optimization framework to closely integrate mocap and SLAM, enhancing the tracking accuracy and the system robustness. Third, we propose dynamic map point confidence in a key algorithm in our method, the bundle adjustment. Next, we will introduce the background, methodology, and results. Human and environment are two important components of our world. Human motion sensing and environment sensing techniques have been extensively studied and used in many applications. We believe that if the human movements and the environment can be simultaneously perceived, such a technology will bring many new possibilities, such as accurate human localization. But most existing works study them independently. On the human side, motion capture based on sparse inertial sensors is recently studied as it is lightweight and egocentric. While this work either do not model the environment or assume a flat ground, which makes them hard to localize the human in a scene due to the drift problem. For environment sensing, monocular SLAM is a well-known technique which can localize a moving camera and simultaneously reconstruct the scene points or structures. While similarly, human prior is rarely considered in SLAM works. As human is often the one that is operating the camera, the movement of the camera should be constrained by the human motion. Our work jointly considers human and environment. We focus on an important and fundamental problem that we believe is common to both inertial mocap and monocular SLAM, which is the localization problem. Human localization suffers from drift in inertial mocap, while it is unstable in monocular SLAM. By integrating human motion prior, SLAM can become more stable as it no longer solely relies on vision. And simultaneously, the stable positioning information is fed back to the mocap module to reduce the drift. And finally, our combined system can achieve accurate localization. This design takes inspiration from real human behaviors, as humans use their body to move and their eye to sense the world. The most relevant works are HPS and HSC4D, which perform human mocap and localization. However, both works use a full-body 17 IMU setup and employ a LiDAR for scene reconstruction or otherwise require pre-scanning the scene. While we only require 6 IMUs and a camera, without the need for a prior scene scan. Furthermore, our method runs in real time. Here we demonstrate the real-time localization accuracy of our system. the human starts from point A and performs various complex motions, including jumping, crawling, and quick turns. After covering a distance of 70 meters, the person successfully returns to the starting point with little drift. Next, we come to our method. Our task is to estimate human pose and localize the human in the reconstructed scene. The input includes acceleration and orientation measurements from the 6 IMUs and the color image captured by the head-mounted camera. Our output includes human pose, localization, and reconstructed map points. Our method incorporates 4 modules. First, the initial mocap module estimates human pose and the coarse global translation. As the camera is attached to the head, a coarse camera pose can be predicted. This module is implemented based on our previous work, Physical Initial Poser, with some modifications to adapt to our task. Then, the camera tracking module leverages the image to refine the camera pose. We first detect all features from the image, denoted as the yellow points. Then, by matching the 2D key points and the reconstructed 3D map points, we can optimize the camera pose by projection. In this step, we fully utilize the human prior. The camera motion should be constrained by the head motion, which is estimated in the mocap module. Thus, we can refine the camera pose by minimizing the reprojection error while satisfying mocap constraints. This optimization eliminates most drift in the camera position. Next, with the refined camera pose, we can update the human translation in the updater module. This is implemented based on a prediction correction algorithm, where we first predict the human position by accumulating the mocap translation. This prior prediction suffers from drifts. While with the refined camera pose observation, we can correct the drift to get an accurate posterior estimate of the human localization. Finally, we have a module to perform mapping and loop closing. We first triangulate new map points from different views. Then, we jointly optimize recent camera poses and the visible map point positions, which is typically called bundle adjustment. We also exploit human prior by constraining the camera orientation and translation based on the estimated human movements from the mocap module. And further, we propose mocap-based map point confidence to dynamically balance the reprojection and mocap constraints in the optimization. In addition, we detect loops in the camera movements and perform post-graph optimization to close the loop. Similarly, in this step, we use the human motion to get the optimization, which improves the accuracy. All these 4 modules combine to form our method, and we utilize some well-known techniques to accelerate our method, which finally enables real-time performance. Finally, we show our results. We first compare our method with previous sparse IMU-based motion capture work. We show the results on HPS dataset. The ground truth motion is shown in green and ours in white. The other colors represent previous works. We can see that all subjects start from the same position, but the other method quickly drifts in the global position and penetrates the scene. In comparison, our method has the best localization accuracy. We then make a thorough comparison with monocular and molecular inertial OrbSLAM3 on total capture and HPS dataset. This table shows the localization accuracy, and we achieve the lowest error. As for the mapping comparison, we evaluate the map point error in 3 synthetic scenes. We use blue points for small error, while red points for large error. We can see that in all the 3 scenes, our method achieves the best mapping accuracy. We also conduct some live demos to demonstrate our system. For visualization and evaluation, we pre-scan the scene and place some landmarks in the scene. The people moved between the marked locations, and as shown in the laptop in the bottom left corner, our algorithm precisely estimates the human locations. Note that the scene is not used by our method. It is only used for visualization. Thank you for your watching. Please scan the QR code to visit our website for more details.